Electronics Pariksha channel. Today we'll discuss a few more problems from diode circuits of analog electronics. Okay. Now we'll see the question. In the following circuit diagram, if the input voltage V1 is less than or equal to VR1, VR1 is the reference voltage. The output voltage is. So this is V1. He has given the condition V1 is less than or equal to VR1. In the circuit, if you see, we have two diodes, D1 and D2. D1 has the positive reference voltage of VR1 and D2 has the positive reference voltage of VR2. If you observe carefully, D2 N terminal is connected to positive terminal. So D2 is basically reverse biased. We have to say D2 is basically reverse biased. So he is giving the condition V1 is less than or equal to VR1. So if you observe carefully, in based on the conditions, we can tell that D1 is usually forward biased, D1 is forward biased, and D2 is reverse biased. Okay, it is very clear from the conditions given. So if D1 is forward biased, and if you redraw the circuit, this is the resistance R, D1 acts like a closed switch. This is the reference voltage VR1, and D2 acts like an open switch, and reference voltage VR2. So what will be the output voltage? The output voltage will be equal to VR1. The same VR1 voltage appears across the output like this. If you apply KVL in this way, output voltage will be equal to VR1. Here we are assuming the diode D1 as ideal diode. So the answer is option A. We'll see the next question. A half-wave rectifier is used to supply 50 volt DC to a resistive load of 800 ohms. The diode has a resistance of 25 ohms. What is the required AC voltage? So this is basically a half-wave rectifier. This is the primary winding and this is the secondary winding. A diode D is placed and this is the load resistance RL. He has given load resistance is equal to 800 ohms and diode forward resistance RF is equals to 25 ohms and DC voltage, output DC voltage as 50 volts. So here from this we can easily find out VDC is basically is equals to IDC into RL. The average voltage is equals to IDC into RL. Now IDC, that is the average current, is equals to Im by pi. This is the basic formula that we already know. Im is the maximum current and pi. So Im, how to write Im? Im can be written as V maximum divided by resistance. But here we have to consider two resistances. One is load resistance, another is diode resistance. That is Rf plus RL multiplied by pi RL. This is the formula. So now we have VDC is equals to Vm divided by Rf plus RL into pi multiplied by RL. If you substitute the values, you will get V maximum we do not know. Rf plus RL is nothing but 800 plus 25 plus 800. Okay. Diode forward resistance and load resistance. Pi and load resistance is 800 ohms. Whereas VDC value we know. VDC is nothing but 50 volts. So 50 is equals to like this. So from this, we'll get V maximum as 51.562 pi volts. That is the V maximum we require. So the answer is option B. Now we'll see the next question. A bridge rectifier uses a 9 volt AC input voltage. The diodes are ideal, and what is the DC output voltage? So here given the input voltage VRMS as 9 volts. So VRMS formula we know for a full wave rectifier is Vm by root 2. So Vm is equals to VRMS multiplied by root 2, that is 9 root 2. So he is asking the DC output voltage. So the DC output voltage is nothing but V average, that is VDC, is equals to 2 Vm by pi. If you substitute Vm value here, 2 into 9 root 2 by pi, which is equals to 8.1 volts. So the answer is option D. Now let's see one more question. A full wave rectifier with a center tap transformer supplies a DC current of 100 milliamps to a load resistance of 20 ohms. The secondary resistance of a transformer is 1 ohm. Each diode has a forward resistance of 0.5 ohms. What are the RMS values of signal voltage across each half of the secondary load as well as DC power supply to the load? Good. Now here in the given question, he is discussing about the center tap full wave rectifier. This is the primary winding, secondary winding, and there are two diodes D1 and D2. Both are given to the load resistance RL. So here the diode forward resistance is given as 0.5 ohms. Here there will be ground. Forward resistance is equals to 0.5 ohms. Okay, the load resistance is given as 20 ohms, and here we have to collect the output voltage. So if you take all these things, the IDC, the average current, is given as 100 milliamps in the question itself. So from this IDC we have 2 Im by pi is the formula that we have. So 100 milliamps is equals to 2 Im by pi, whereas Im is equals to 50 pi milliamps. This is the maximum current that we get. So now IRMS is equals to Im by root 2. For a full wave rectifier, IRMS is equals to Im by root 2. So 50 pi divided by root 2 is equals to 1107 milliamps. This is the RMS current that we have got in the center tap full wave rectifier for the given circuit. Now we have to find out VRMS, because he has clearly asked what are the VRMS values of signal voltage. So in order to find out VRMS, we need to find out IRMS first. That's why we have found IRMS. Now if you look at VRMS is equals to IRMS. RMS current flows from the secondary winding, diodes, and load resistance. So three resistance need to be calculated. So resistance like secondary winding resistance, diode forward resistance, plus load resistance. All three resistances need to be calculated, need to be considered. So if you substitute 1107 milliamps, that is 10 to the power minus 3. Secondary winding resistance is 1 ohm. Diode forward resistance is 0.5. And load resistance is 20 ohms. Then VRMS will be 2.39 volts. So this is the VRMS voltage that we have got. Now he is also asking to calculate the DC power supplied to the load. So DC power supplied to the load, PDC is equals to I square DC, that is square of average current multiplied by load resistance. I square DC is already given in the question only, that is 100 milliamps, 10 to the power of minus 3 whole square, into load resistance is 20. The answer will be 0.2 volts. So now the VRMS is 2.39 volts and PDC is 0.2 volts, 2 watts. So the answer is option A. Now we'll see the next question. A full wave rectifier, a full wave rectifier uses the internal resistance of each diode 20 ohms. The transformer RMS secondary voltage forms the center tap to each end of secondary is 50 volts and the load resistance is 980 ohms. Mean load current is. So he's asking to find out IDC. For a full wave rectifier using two diodes means it is a center tap. It is a center tap rectifier. Okay. Now we'll just draw the diagram. This is the primary winding. This secondary winding, diode D1 and D2. Every time I draw these circuits because it will be a practice for you. So diode forward resistance is given as 20 ohms and load resistance is given as 980 ohms. Now we have to calculate IDC, whereas IDC is equals to 2 Im by pi. We do not know what is Im. So to find out Im, we have a formula Vm divided by Rf plus RL. Here, why we consider Rf? Because the Rf value is given in the question. That's why. Now, V maximum. Here, the secondary voltage is given as 50 volts. That is the RMS voltage. So, RMS is V maximum divided by 2. VRMS is equals to V maximum divided by 2. Then V maximum will be VRMS root 2. So, substituting this here, VRMS root 2 divided by Rf plus RL. VRMS is 50 volts, root 2 divided by 20 plus 980. Now, substituting this value here in IDC, that is I average is equals to 2 Im by pi. Here, what will be this value? 50 root 2 divided by 1000. So it is root 2 divided by 20. Root 2 divided by 20 divided by pi. So the answer will be 45 milliamps. Answer is option C. Now we'll see the next question. A 40 volts DC supply is connected across network comprising Zener and silicon diodes. The regulated voltages V01, V02 and the source current ISR. So he's asking to find out V01, V01, V02 and the current IS that is here, the current that is flowing here. Let's calculate it. Here, if you observe, the cut-in voltage of Zener diode will read out the circuit. This is the 40 volts input voltage and this is the resistance 1.5 kilo ohms and this is the Zener diode Z1. This is a silicon diode and this is again a Zener diode. Two Zener diodes are placed and he's asking to find out the output voltage here. So here if you observe carefully, here the cutting voltage is 6 volts. Here for the second Zener diode, it is 3.3 volts. The silicon diode in between has a cutting voltage of 0.7 volt. So all put together, we have 10 volts here in this branch. It is 10 volts. So the input voltage is greater than 10 volts. Input voltage Vi, which is greater than 10 volts. So there is a possibility for the current to flow in the circuit. There is a possibility for the current to flow in the circuit. So circuit conducts. So by applying Kirchhoff voltage law, simply by applying KVL, you will get 40 volts is equals to 1.5 kilo ohms into IS. IS is the current that is flowing here. Minus 6 volts minus 0.7 volts minus 3.3 volts. So if you solve the circuit, IS will be is equals to 20 milliamps. So when IS is 20 milliamps, what will be the output voltage? The output voltage is simply the voltage across this branch, that is 10 volts. How it will be? The Zener potential, Zener diode potential Z1, VZ1 and cutting voltage of silicon diode V gamma plus Zener potential of second Zener diode potential, that is 6 volts plus 0.7 volts plus 3.3 volts. That is equals to 10 volts. So output voltage is 10 volts and current is 20 milliamps. He is asking you to find out the voltage here also. Even this part of the voltage he is asking. That is V01. That is 4 volts. zero point 0.7 plus 3 volts. Okay. This is V02 and V01 is equals to 0.7 volts plus 3.3. That is 4 volt. Okay. So 4 volt, 10 volt and 20 volts. Answer is option D. So crest factor, if you see the next question, the crest factor for an alternating current source is the ratio of, crest factor is nothing but a peak factor. Peak factor or crest factor, both are same, which is the ratio of peak value, that is Vm, divided by RMS value. It is the ratio of peak value and RMS value, that is Vrms. So if you see here, for the half wave rectifier and full wave rectifier, peak value will be Vm only. Peak value will be Vm, that is common, Vm. Whereas RMS value is, this is Vm by 2, this is Vm by root 2. So if you take the ratio, the crest factor will be, this is 2 and this is root 2. Like the video, share the video and subscribe to the channel for better content and more videos. So the input to a bridge rectifier is 230 volts PRMS and 50 Hz. The DC output voltage and the ripple factor with the load resistance 100 ohms and capacitor filter 1000 microfarads is. So this is a bridge rectifier. Bridge rectifier contains 4 diodes in a diagonal shape. So if you draw the circuit, it will be like this. There will be 4 diodes, diode G1, G2 and D3 and D4. So the output is taken from here. This output is connected across a capacitor C and a load resistance Rn, D3 and D4. This is primary winding where the input is given. That is secondary winding. So here in the given circuit, we know that given data is Vrms is given, that is 230 volts. So from Vrms, we can find out V maximum. V maximum is nothing but Vrms multiplied by root 2. So V maximum is 230 root 2. And VDC, the average output voltage will be 2 Vm by pi for the full wave rectifier. So it is 2 into 230 volts multiplied by root 2 divided by pi, which is equals to 207 volts. So this is the average output voltage. Now, ripple factor. He is asking us to find out the DC output voltage, that is average voltage, and the ripple factor, both. DC output voltage is found and the ripple factor. Ripple factor of a bridge rectifier, bridge full wave rectifier of a capacitor filter is given as Rf is equals to 1 divided by 4 root 3 F frequency, that is capacitance C, into RL. So substituting the values, 4 root 3, frequency is 50 Hz, capacitance is 1000 microfarads, and the load resistance is 100 ohms. So with this, you will get ripple factor Rf is equals to 0.028. If you have any doubt how this ripple factor formula is derived, we'll see the derivation of this ripple factor formula also. This will be useful for your examinations and memorizing purpose. If you see here, derivation, the output voltage will be like this. for a full wave rectifier, the output voltage is all the input will be converted into output voltage without any lapse. The half wave rectifier, only one half of the cycle will be there, but in the full wave rectifier, both cycles will be there. And the capacitor, as a capacitor input filter is used, capacitor charges like this and discharges. Again charges, discharges, charges and discharge. This is the charging and discharging cycle of the capacitor. So if you consider this is the ripple voltage, this particular portion is nothing but ripple voltage VR. The ripple voltage VR is given with the change in the charge of the capacitor. The change in the charging and discharging happens, no, the change in the charge of the capacitor. Whereas the change in the charge can be given as IDC into time period. We know that famous formula. The Q is equals to IT is the formula. So here the average current flows. T is the time period. What is the time period of the output cycle here? This is T by 2, half of the input. The time period will be half of the input waveform, that is T by 2. So the time period is here is T by 2. So it will be written as T by 2. This is delta Q multiplied by capacitance. So here the time can also be written as reciprocal of frequency. So IDC divided by 2FC. This is the ripple voltage of a full wave rectifier with capacitor as a filter. Now, VRMS. What is the VRMS of the ripple voltage? VRMS of the ripple voltage. If you observe the ripple voltage, it is similar to a triangular waveform. Okay, if you observe the ripple voltage, it is similar to triangular waveform. So the VRMS of a triangular waveform needs to be taken. So VRMS of triangular waveform is nothing but VR divided by 2 root 3. So here, which VR, substituting VR, we'll get IDC divided by 4 root 3 into FC. IDC can also be written as VDC divided by RL. So 4 root 3 F dot C dot RL. This is the RMS value of the ripple voltage and the ripple voltage. So now the ripple factor. Ripple factor is nothing but the ratio of ripple factor gamma is the ratio of RMS value of the ripple divided by VDC. So RMS value of the ripple is VDC divided by 4 root 3 F dot C dot RL divided by VDC. So you will get 1 divided by 4 root 3 F dot C dot RL. This is the ripple factor of a full wave rectifier with a capacitor input filter. Okay, hope you understood this session. Please like the channel. Please subscribe to the channel, like the video and share the video. You will get better content and this will give us more encouragement to give the awesome problems to you. Okay, thank you.
Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.